All right, let's look at how to solve linear programming problems graphically using Desmos.com. So here are the problems that were considered in the previous two videos that I shared with you. And we visit Desmos.com, www.desmos.com, and you can click Start Graphing, and we can learn how to solve these using those methods from those videos, but do it ourselves. So the first thing we'll start out by doing is plotting the constraints. And so I'm going to start with this x plus 2y is less than or equal to 16. And I just type x plus 2y, you don't have to include the asterisk for multiplication, is less than or equal to. When I press less than and then I press equal to, then it changes from a regular less than sign. When I press equals, it changes to a less than or equal to sign. And then I press 16. And this shows us in red the feasible region for this constraint, I should say, the region that satisfies this first constraint. Everything below this line in red satisfies that constraint. Then we can click on the next line here and add the next constraint. 5x plus 3y is less than or equal to 45. And we have now the blue region satisfies the second constraint. And the intersection between these two regions, the boundaries are here, these satisfy both of the constraints. Let's add our non-negativity constraints. X is greater than or equal to 0, and we can add our y is greater than or equal to 0. And we can see that the intersection of all of these is our feasible region. Now, it's kind of difficult visually to identify what the feasible region is when you've got so many colors intersecting. So what I like to do to better see the feasible region as distinct from the infeasible region, which is everything outside, is to turn all of our equality constraints around. So we shade in the infeasible parts of the plane. So I'm going to change this less than into a greater than or equal to constraint. I'm not changing the problem. I'm just abusing Desmos.com to visualize it differently for me. I'm going to change this less than to a greater than or equal to. I'm going to change this greater than to a less than or equal to, and I'm going to change this greater than to a less than or equal to as well. Less than or equal to. And now you can see that by flipping all of these around and with shading the infeasible parts of the plane, we're left with white in the area that is feasible. This here is now the feasible region. Everything that's outside, that's shaded in, is infeasible for one reason or another. This region here is infeasible because of that, I think that was the first constraint that we drew. Yep, the first constraint that we drew, this red is infeasible, yep, corresponding with this constraint. This region here is infeasible because of the second constraint. This region is infeasible because of both, it violates both of these constraints. And then the next thing that we can do is write our objective function. Now, this is kind of following the approach. We could click on each of these here, right? Each of these intersection points, and we could find out, okay, 9, 0, and we could evaluate the objective function. So here, we can do that. We've got our 4 points, our 4 extreme points. We can evaluate the objective function at each. 0, 0, 2 times 0 plus 5 times 0 is 0. We're trying to maximize something, so looks like 9, 0 is going to do better than that. 2 times 9 is 18, plus 5 times 0, that's 18. Okay, so that's the best we've got so far. 6 and 5. 2 times 6 is 12, plus 5 times 5, oh, that's 25. That's a bigger number. I think that that's going to be our winner. It's evaluated in the previous video. I'm not going to do all the mental gymnastics. So let's start with the second graphical solution approach, which is drawing that objective function. Instead of evaluating all of the extreme points according to the objective function, we're going to draw a line of constant value of the objective function. And the suggestion here is that we do 5x plus 7y and he said in the video to make that equal to the product of the coefficients, 35, and that typically is a good value. And then what we're going to do is we're going to sweep that line. We're trying, this here, what does this mean? This is all points, 7, 0, 0, 5, this is all the set of all points. This black line is the set of all points for which the objective function is equal to 35. There are certain points that are inside the feasible region. 7, 0, and 0, 5 are inside the feasible region because these are greater than or equal to constraints here. So they're inside. Everything outside here, those also have values of the objective function equal to 35, but they're not feasible, so we're not allowed to use them. But that means that we can easily see, here's all the points that we can possibly choose that are inside the feasible region for which the objective function value is equal to 35. Now 35 isn't special to us. We want to get a greater objective function value. So let's see all the points that have an objective function value that's equal to 40. All the points with an objective function value equal to 50. All the points with an objective function value equal to 60. And we can sweep this up little by little until we find that, look, we've almost entirely, all the points are almost infeasible now. There's just one point left, 6, 5, that is still within the feasible region. If we go above that, any objective function value greater than that, none of the points are feasible. Below that, there's lots of feasible points. But once this is going to be the optimal value of the objective function, because this is the farthest up we can sweep this line before it leaves the feasible region. There's only one point left, and so that's going to be our optimal solution, 6, 5, as we expected before. We'll do quickly another example, so I can clear my axes, and I can plot the constraints of the second one. X plus 3y is greater than or equal to 6. 5x plus 2y is greater than or equal to 10. And y is less than or equal to 4. And x is greater than or equal to 0. And y is greater than or equal to 0. And we want to flip all those around. This is going to become less than or equal to. This is going to become less than or equal to. Greater than or equal to. Again, just for visualization purposes. Now we can see that the feasible region is here. This white area is the feasible region. And so let's draw our objective function line corresponding with, we're going to say, the product of the two coefficients. So we'll say 5x plus 7y is equal to 35. Is equal to 35. This is a minimization problem, so we're going to keep on reducing this. 30, 20, 18, 17 and a half. We want to find exactly the value that gets us right where we want to be here. And sometimes that can be tricky. 17.6, 17.7. We're getting closer and closer. And so what we can do is we can see that we're going to leave the feasible region here. Let's get this out of the way, and we can just find what the intersection of these two constraints is. And it tells us right there, 1.385, 1.538. And that's going to be our solution. And the objective function value is equal to, well, we can just evaluate the objective function at this point.